In this video, we introduce functions. A function from the set of x values to the set of y values is a rule or formula where x values are input and the function assigns exactly one y value to each of those x input values. We call the set of all x values, or all possible x values that we input, the domain. We call the resulting y values that we get, and we plug the x values in, the formula calculates values, and those are our y values. This calculated set of values is called our range. And here's some examples of functions and non-functions. First, y equal 2x plus 1. This is a function. It's a linear function. Any x we put in there is only going to give us one answer. Clearly, only one answer. Now look at the next one. Absolute value of y equal x. If we let x equal 9, y can equal 9 or negative 9 because we're taking the absolute value. So y takes on two different values. So this is not a function of x. In the next example, y equal x squared. Some students say this is not a function of x, but really it is. Each x value gives you only one y value. When x is 3, y equals 9. When x is negative 3, y equals 9. We only get one y value per x value. It's okay to have two different x values resulting in the same y value. It's still a function of x. Now in the next equation, y squared equal x, that's not a function because if x equals 4, like I have here, y equals either 2 or it could equal negative 2. We have two values of y corresponding to one value of x, so it's not a function of x. Function of x only gives you one answer. And in the last example, y equal plus or minus square root of x, that's also not a function of x. If x is 4, y equals 2 and negative 2. And if you notice, the last equation is really a rewrite of the one previous. We take square roots of both sides of y squared equal x, and we get y equal plus or minus square root of x. Now let's take a look at function notation. If our formula is a function of x, we may replace y in that formula with f parentheses x. And we call that f parentheses x parentheses f of x. And f of x means the y value when x is input into the formula. So if we have y equals 2x plus 1, that's a function of x, and we can write that f of x equals 2x plus 1. That's our function. Now here's another thing about this notation. If we want to find the value of y when x is 3 and our formula is 2x plus 1, we just write find f of 3. It's shorthand. It just saves a lot of space. And f of 3, when our formula is 2x plus 1, is 2 times 3 plus 1, or 7. If we want to find the y value when x is negative 5, we say find f of negative 5. And here we see f of negative 5 for our formula 2x plus 1. We replace the x with negative 5, and we get 2 times negative 5 plus 1, which makes negative 9. And we could even plug in variables. Find f of capital A means replace x in our given formula with capital A. And what we get here is 2a plus 1 as an answer. And as I have written here, just remember to replace each x in our given formula with that value that follows f in the parentheses. Here's a few more examples down below. Let's start with a new formula. Now our formula is f of x equals x squared plus x. And we want to find f of 5. To find f of 5, we plug in x equals 5 in the first place x occurs, and we square it. And we also plug in 5 where the second x occurs, because it's x squared plus x. There's two different places where x is occurring in the formula. So we get 5 squared plus 5, which makes 25 plus 5 equals 30. So f of 5 equals 30. Now let's try to find f of x minus 1. We replace each x in the formula, x squared plus x with x minus 1. So we get an x minus 1 quantity squared plus another x minus 1. The x minus 1 quantity squared, when you FOIL it out and combine like terms, you get an x squared minus 2x plus 1. Then we add that to an x minus 1. And we end up with x squared minus x. The ones cancel. So let's try f of h minus 1. Well, in f of h minus 1, we plug h minus 1 in each place where there's an x. We get h minus 1 quantity squared plus an h minus 1. We square out the h minus 1. We get h squared minus 2h plus 1. We add an h minus 1 to that. Then we combine like terms. The ones cancel again, and we get h squared minus h. Oftentimes, we'll use notations other than f of x. If we have a bunch of different functions, like say 3 different functions, we don't want to call them all f of x because there are 3 different formulas that are used. We might call one f of x, we'll call g of x the other formula, and maybe if there's a third one, we'll call it h of x. And oftentimes we'll use other notations like p of x if it's population. And if the variable is time, if the independent variable is time, oftentimes instead of x, we'll use t. So p of t will often represent population as a function of time. I have an example at the bottom here. If p of t equals 3t squared, represents the population p as a function of t in years, then p of 5 would equal 3 times 5 squared, which equals 75. What we're really saying here is the population at 5 years will be 75. We're really saying the same thing as f of x equals 3x squared, or without the function notation, this is really the same as y equals 3x squared. But by using function notation, we give a label to the formula. It's possible to have functions that are defined in terms of 2 or more parts. And I have an example here. F of x equals x squared plus 1 if x is greater than or equal to 1, and it equals x plus 1 if x is less than 1. This means that if the input value is 1 or more, we use the top formula. If the input value is less than 1, we use the bottom formula. And I've done a few sample values below here. If x is 4, f of 4 will use the top formula, and we get 4 squared plus 1 equals 17. If the input value is x equal -1, we use the bottom formula, and f of -1 is -1 plus 1 is 0. I've graphed this function. The left part is a straight line, and you can see this point, x equal -1, y equals 0. It's right here. And we also see when x is 0, y is 1. So we have the straight line part on the left, and then the quadratic part starts at x equal 1. We haven't really graphed quadratics much here yet, but it's a graph that's a little bit different than the linear part. We're going to look at finding the domain of a function. As I have written here, the domain of a function consists of the largest set of input values that results in a real output value of the function, unless otherwise restricted. With a function where y is a function of x, we are looking for the largest set of x values, those are our input values, that makes y, the output value, a real number. To see how this works, let's look at an example. Find the domain of f of x equal 1 over x minus 1. Here we want to find the largest set of x values that makes 1 over x minus 1 a real number. Now the easiest way to do this is to find all the x values that make it not a real number. And the only x value that will do that is x equal 1, because x equal 1 results in 1 over 1 minus 1, which is 1 divided by 0. So x equal 1 will make it not a real number. So our domain is going to be all real numbers except that value that we determine that would not make it a real number. So the domain is all real numbers except x equal 1. Now there's a variety of ways to write that answer. We can write it all real numbers except x equal 1. We can write that answer in interval notation, the interval from negative infinity to 1, not including 1, in union with 1 to infinity. We can also write the answer as all reals, comma, x not equal to 1. And some books will just say x not equal to 1. I have a hint here at the bottom, and you should really read this hint again and again if you're having problems with this. The way to find the domain of a function is to first find all the values of x that don't result in a real value of y. And the domain will almost always be all real numbers except for these values you found. And here's another example I have down here. For the function y equals square root of x equals a negative value gives you a non-real value of y. 0 is okay, but no negatives. So the domain is going to be all real numbers except the negatives, which is really 0 and all positives. So the domain of y equals square root of x is all reals except negative numbers, or we can write that x greater than or equal to 0. Sometimes we're going to restrict a domain even further than we showed in the last example. For example, if we have a function where x represents the number of people visiting a shopping mall, we're not going to use a negative value for x. We're going to use positive values. In fact, we might even restrict the values to positive whole numbers.